about the robot.
It tells you how accurate it is, what's the record of it.
Well, how accurate it can go to, how accurately or precisely it can go to a position, right? So what's the difference between accuracy and repeatability?
Accuracy is how many times does it right.
Well, you got it backwards. Accuracy is a one-shot deal, right? No. So I've got a new robot that's out there and it runs off mechanical stops. Mechanical stops can be extremely accurate. Extremely accurate. So just because, but understand the accuracy in that situation would be how precisely somebody can place a stop. So when we talk about accuracy, you say, well, how accurately can you position this robot? And that would be accuracy would come into play then. But accuracy is how accurately the accuracy or precision the robot has to go to a spot. We refer to them as points, which is the same thing, right? And repeatability is how many times it could go back to that spot when it's given a command with a program. Okay, you understand? So I might come in and bring it down one time, then I go away. That would be accurate. If I constantly come back to that same point over and over and over and over again, and how precisely it hits that spot will be repeatability. You understand that? What's payload? Yes, and what people don't understand is that's without the tool attached. So that's the lifting capacity or the moving capacity of the robot. If you add a tool on there, so if it's got a payload of 500 pounds, and you put a 100-pound tool on there, you can only pick up 400 more pounds, right? So that specification on these robots, because when FANUC makes a robot, they have no idea what type of tool you're going to mount on that thing. So robot manufacturers are not usually in the tooling business. They make robots. Right? You understand? They make the robots, but they put a plate out there that the end user can mount tools on. And of course, so when you put a tool on there, that's going to subtract from your payload. Right? You understand? Yes or no? What you're trying to pick up. Speed.
Maximum rate.
Yeah, and what we got to understand, speed specifications are given two ways. For linear action, they're given distance per unit, right? You understand? When we get into rotary axis, their speed is given in degrees per unit. The two main units that we use in robotics, of course, is the English Standard Unit, which is what most of us know how to use. And then, of course, the predominant is the metric system. So that's why in this class we're trying to get you into the metric system. In fact, the first hands-on lab we'll do, I'm going to try to do that in class, is when you do these specifications, it's going to ask both ways. It's going to ask in millimeters and it's going to ask in degrees. And you don't get to choose which one. You got to do what? Both. And that's a big thing that we have in this class. That people come up and they'll fill in the blanks, and all they put is inches per second or something like that. And of course, they start missing because right down below that is asking centimeters. So remember that when we do the lab and start recording these things. What other specifications did we talk about? They won't pop in my mind right now. So the first specs that we're going to talk about, the first lab we're going to do, first hands-on lab. We have 3 homework labs we do. Y'all supposed to do one today. And then we'll have one that's due. I'll give y'all the other one out. That'll be due when we come back on Tuesday. And then we'll give out the third one Tuesday, and they'll be due when you come back on Thursday. So what are the specs? Anybody remember? Because they don't follow mine. So what you see? Repeatability, accuracy, payload, speed. The other thing that is specified, of course, is the power sources available. So all our robots over here use electric power, but they're also piped for pneumatic. So you look at the robots, you see that except for the ABD, I think the ABD is struggling to sign. We'll go look at that. I think. We will look at the pneumatic tubing. Y'all can look at our robots up there. You see the pneumatic tubing going to the gripper. The tubing goes back to the robot, right? And then, of course, if we look down at the base of the robot, we'll see that there's a connection for the actual pressure. So our robot, all these robots, even though the motors run off electricity, they're piped. They have the piping unit on that. Because the predominant power source for cooling is pneumatic power. What's pneumatic power? I'm listening. It's you just can't say air. It's creating pressure with a gas. So if we have a power source is used to create force, right? So when we use pneumatic, we create pressure with gases. In hydraulics, we create pressure with what? Fluid. And of course, why is pneumatics the most widely used? Could, definitely. It was probably one of the main reasons it's safer. And probably one of the big reasons it's cheaper to use. Yeah, that was the dangerous stuff. Hydraulic pumps on the airplanes I worked on when I was in the Navy. There was 2 of them, 3,000 psi pounds per square inch. You saw a pinhole, you didn't reach down there and put your hand because it was strong enough to just go right into your finger. You don't want hydraulic fluid inside your knee. I've heard of horror stories where people's arms have rotted off and stuff like that because they got hydraulic fluid. So pneumatics is cheaper. Pneumatics is safer. And why is it cheaper? Because in hydraulics we have to use a lot of metal tubing because of the pressures. And or reinforced piping, rubber piping, and that's very expensive. You don't believe that your air conditioning system in your car is a hydraulic system. Almost all the piping in there is metal, except when it goes from your body over into your engine, right, and then from your engine over to the compressor. If you ever have to replace one of those tubes, need to be ready. Not cheap. Because they're reinforced rubber tubing. They're very, very high pressure. In pneumatics, we predominantly use plastic. Another reason why pneumatics is cheaper, because the predominant gas we use in pneumatics is air. So we don't have to have a tank to hold the air. Well, that's not true. We can pull the air from here, right? You understand? And when we get through with it, using it, what can we do? Yeah, we can exhaust it back out to here. Right? You understand? So what's the advantage of hydraulics over pneumatics? Yeah, well, the amount of force we generate, which basically translates directly to how much work we can do. The amount of force we generate is equal to, as soon as I get my PowerPoint up so I can draw. The amount of force we can, generate. Dell, I got it open in my office. Oh yeah, we scale because we don't give makeups on the lab, so we scale it by one lab. Yeah, I can understand that. Yeah, so this lab shouldn't hurt you as long as you don't miss out anymore. Yes, sir. Yes, sir. Yeah, so I understand what you're going through. Well, I have a feeling of what force we generate in a pneumatic system. Anybody know? My computer's giving me problems this morning. So the amount of force we generate is equal to, force is equal to area times pressure. So force is how much surface area that the pressure is pushing against. And this generates force. So you can see that the higher we make the pressure, the more force we create for the same area. Or we can raise the pressure and lower the area to create the same amount of the equivalent force that we would in pneumatics. So that means we were running planes that I were working, used 3,000 psi for hydraulic fluid pressure. So that means it could generate 3,000 pounds of force with 1 square inch of area. Now the problem with gases is when you start pressurizing them, they want to turn into a liquid. So this is why we don't run gases at a real high pressure, because they'll liquefy. Air is great, but the problem we have with air is that it's got a lot. First, gases have to be, so this is one thing we have to do with liquid. You don't have to, they're pressurized when we use gases, we have to pressurize before we use it. So we can't create a pressure out of a gas until we pressurize it. So this is why in pneumatic system, you got these units they call compressors. So to get a pressure out of a gas, we have to deliberately put it under pressure, right? And fluids, they generate pressure. As soon as you try to use a fluid, it generates a pressure, right? You understand that? So we have to have a compressor on a pneumatic system. But on a hydraulic system, we got to have a pump. On a hydraulic system, we have a tank that holds the liquid. On a pneumatic system, we have a tank that holds a pressurized gas. Right? So far, the system is basically compatible, right? You understand that. Also, but one of the problems we have in pneumatic is using air. The air has a lot of moisture in it. And air can only hold so much moisture per cubic foot of air. After that, it's drained, right? You understand that? So what happens is when you pressurize it and you make the cubic feet smaller, it can't hold that. It can't hold all that water anymore, so it releases that water inside your tank. So anybody who's had a compressor, one of the preventive maintenance things you do all the time is drain that tank. Huh? Remember. It becomes obvious after a while because it will start you start using your blower to be spraying out the gas, and you realize your compressor is running a lot because you're increasing the size of the tank. So you don't have the capacity that you have anymore. The compressor we have next door has a dryer on it. It also automatically drains. Huh? Yes. You can hear it. Yeah, you can hear it in there every once in a while. You'll hear it kicking in your. So this is why. So hydraulic is dangerous because it's under such high pressure. Hydraulic is a more expensive system. So we still have a tank, but on the hydraulic system, every valve you have and everything, every actuator you have, we have to return that all the way back to the water, all the way back to the tank. Pneumatic systems, when we get through with it, that uses the air and the gas. When we get through with it, we just shoot it back out in the air. So we'll see that. So what power sources are available or can be used by the robot? Like I said, the predominant source for the actual robot, the controller, by the way, the controller is a computer. Computers don't run off gas and they don't run off fluid. So the controller has got to be it's got to be there. The robot that actually powers the actuators are that device that takes the pressure and converts it into motion. That's an actuator. The actual actuators on the robot predominantly are electric. But most of them are set up so you can utilize pneumatic pressure for the tool. Are you okay? Some of them have the control valve inside the robot, which the fan can be cook it.
You mentioned a battery the other day, it's like $250. What is the battery used for that?
What happens is that when we say most robots, not all of them, but when we do these points, they're saved in what we call a Cartesian system. TI. Yeah, I don't think that I's in there. A Cartesian system means it's a three-dimensional plane. It's hard to draw them in and out, or we can move between the planes. And we always reference it from what we call a point of origin. So that would be like you're trying to give somebody direction. You say, well, how do you get so and so? I say, you go down 4 red lights and you take a right. But I was talking in Huntsville, and you're down here in Vestal. So normally when we give, so now I get directions, so you go out this front gate, it's gate right here. So that's my point of origin, right? You understand? So once I've established a point of origin, the directions make sense. If you don't establish a point of origin, the directions don't make sense. I had one guy, I worked at a scale company, maintained electronic scale, and he gave all his directions for eating places. You go down here to McDonald's, or you go over here to Burger King, you do this. He must have knew where every eating place was in the state of Alabama. And then we record that, and this axis, the up and down, we're going to refer to this as Z. So once from the point of origin, this would be plus Z, and if we go below that, that would be what? Negative Z. From in and out, this is X, and this would be plus X, and this would be minus X. And then left and right would be plus Y and minus Y, which is real neat. And this is the way they store it. So they'll say, okay, you come up X so many degrees, and you come up, go Y such a distance. So this point right here, anywhere I put a point in this plane, it could be identified by these 3 different things, right? Understand what I'm saying? So I can say points now, or say positions by a Cartesian system. And just about all your robots have to do that. Motor Man don't. We use what we call encoder pulses to say this. But every other robot in here saves it in this cartesian. That's why we have batteries, because that robot, when they ship that robot, it's not connected to the controller. And when the controller's turned off, what's going to keep that origin? So the robot, in the base of the robot, it has batteries in the base of the robot that maintains that origin. So I can disconnect the robot, I can move it around. Those origins are relative. The factory gives you a default origin. It's the default origin on the robot is basically at the center of the base. Then, but you can reteach origins. We have what we call frames. You can reorient the robot on how it records points. So if I'm always working on a slanted surface and I want to come back, I want to set it up so I come back 15 millimeters from that surface, that's all the difference in the world from down here. So what we have the ability to do, we call them frames. And what we can do is we can teach frames. We call them user frames. And from then on, the points are stored relative to my application, not the one that the factory considers to be their application. So that's long. And we'll go over there. We're going to go over there back before we start on this chapter. So what's the main parts of a robot system? Of course, the big is this guy, right? But he's not the guy. Well, what's the guy? What's the person in the robot system that basically controls everything? Huh? The program, but you can't program it without this guy. The teach-pen, you can't, the teach-pen is nothing. So what y'all telling me is what's the main part of the computer? You say, okay, it's the display. You can't say, okay, the main part of it is this guy down is the keyboard. You can't say that. You can't say the main part is the disk drive. You can't say that. The main part, somebody in these computers, we call it a motherboard. But what we do over on the robot is we combine it into a unit. And it should be number one, guys. It's the controller. And we talked about this last class. So that controller is the unit that controls everything you see. So the controller went out on the ABB robot, and now it wasn't a robot anymore, right? You understand? It was a chunk of metal. Let's put it over there. We got some classic robots. Nancy saw these too. Nancy saw these. She was really, they were gifted. Nancy saw them. Said, "Wow," she was thinking about these times right here. She thought it was a battery-powered robot that would come up and teach plastic. It's not. It's plastic. And we can demonstrate axis on it. So you can see all the axis on it. So there's base, there's axis 1, there's axis 2, there's axis 3, there's axis 4, 5, 6. It works good for that. This is not a robot. This is not even a robot, right? So there's no control. Nothing you can do with it. You have to do it right. That she's all excited. I can't even remember where we got it. We got it from maybe, I think it's ABB. Kuka. So the controller, and then somebody said it the other day, we have what we call the teach-pen. And what do we do with the teach-pen? We program. This is where we do our programming. This is what we call it dog profile. What's dog? Moving motors. But manually moving motors. Running motors. We don't move the motors. we run the motors, and the motors are connected to an active robot. We use it to program the robot. We use it to, what we call it teaching, right? We teach programs with it. We modify programs with it. We copy programs. We delete programs. We back up programs with it. Also, we configure the system with it. I think what we talked about is all y'all cell phones have a little button you put on called settings. Little thing on your touch screen. You get that settings, and that's where you can go in and set up your display and do all kinds of stuff. Well, that's what we do with it. So the Teach Pendant is what we call an HMI, which is the Human Machine Interface. I need to put that in y'all. HMI. And what is the interface? Interface is to make a connection. Oh, computer firm. So with the HMI, that is the HMI. The Teach Pendant is the HMI robot. That is your human to machine interface. That's your connection to that robot. We'll go ahead and look at some of this. And then we actually have the robot part. The robot would probably be the third thing. The robot has all of the actuators that converts what? Pressure into motion. Let's go around and look at our robot. And so, first thing we have to do if we're going to teach a job is we have to give it a name. So, so on this one I would go to robot, and then I'd go to controller, and then I'd go to select a job. And then we have to come up with a name, right? So what I'm doing is I'm just going to call it a play. And then when I do that, I've created a job. And then I'll bring up the simulated controller. The simulated Teach Pendant. Now that would have been on the Teach Pendant itself. And this is my Teach Pendant. And what it does is it automatically puts two instructions in there called a no operation and an end. So y'all, what do y'all want to do? So what I'll do is I'll just jog the robot to a position I want it to go to. So I have it on what we call world coordinates. So I'll be able to jog it what we call Cartesian. So I'll just I'll bring Z down, and then I'll teach that point. So I'm going to come over here and say, I think on this one, I'm going to add, and then there's some more other information, so I'm having to enter some things, but anyway, I'm going to come up here and just enter that point, and notice it automatically is supposed to. It won't let me do it. Hold on a second. So it doesn't do it this time. It's not with this. So what I do, I'm going to go to robot, I'm going to go to controller, select a job, and I'm going to come up here and type in a new name. say okay, and then I can go back to my teach pendant. And now I should be able to teach a point. If it don't work, guys, I'm not going to go any further. I'll just figure out this is not this class anyway. So what I would do is I come down here and I position the robot where I want it to go to. Then I come up and select what type of move we want it to be. I select the speed I want it to go at. And that's what you'll learn. You'll learn the type of moves. And then we tell it to add that instruction, and hopefully it'll pop in there. Okay, so there, I just taught a point. And then what I can do is I can move it to wherever else I want to go. So let's just do a plus Y. So I'll come over here and just move it plus Y. And then I'll come over here and select what type of move I want. We'll make this a straight line move. And then I'll teach that point. And then I'll come up and I'll move it somewhere else. So this is what we're doing. We're teaching points, but the points are recorded according to what we refer to as a Cartesian system. And then we'll teach this point. We'll do the same move. And then we'll move it here. Teach this point. And then we'll just take it back up. And there's a lot of tricks we can do with a simulation that we can't do on the real robot over there, which is pretty neat. But anyway, so what I've got, and then we'll teach this point. And then when I get it taught, you can come up here and we can run the program. You'll see that? And that's programming. Now there's a lot of syntax and commands and different types of moves you can do, which we're not going to get into this class. We have to set the speed. And what's nice is that the controller automatically puts the right syntax in there for you. It puts the right way this program is written. So it's not that hard. I mean, it's just that for accurately positioning the robot, and then of course learning what type of move do you want, and what other information is required by that move. And once you learn that, you can teach. And every one of them does the same way. They just call these moves something different. Like I said, Motorman calls it what they call a joint move, and the Kuka calls it a PTP move. No, this is simulation. I don't know of any. You're talking about a $5,000-$6,000 package right here that they don't give away, because this is their robot. This is their robot. Now, I'm not saying there's not some out there that's similar. It might would give you a feel of it, you know, but I don't know. I hadn't researched it in a little while. That would be a good point. I'll go out there and look. These are called simulation programs, robot simulation, and this is called MotoSim. Is the name of this. You can download this off the internet, but you got to have a hardware key to run it. So it don't do any good to get the software. So yeah, they give the software away free. And so this is not a USB drive. This is a dongle, or this is a hardware. We call it hardware keys. So right now, if I tried to create a program, it would tell me I couldn't do it. And that's hard for them to give that stuff. It's hard for them to give that stuff away, because that's a very, very expensive package for their robot. So all they give you is you develop this whole model yourself.
Are you able to create something or program at that nature, save it to USB and transfer it to them to be able to load it up there?
I don't know what you mean.
This program right here that you create simulation.
Yes, that's what we talked about the other day. That's the advantage of a simulation. is that you can crash this thing, you can mess it up, program can screw up, but once you get your program ready in your simulation, you can download that on a removable media. We have to go through 2 steps because we don't have compact flash readers on this computer. So what you'll do is you'll save them on a USB drive, and then you'll run it, then you'll put it on a compact flash card, and that's what that. And what's really, really neat, if you got a good model, you can download a program from the robot and come over here and check it out on your computer. You can check it out on the computer, or not even check it out. You can modify it, but while you're modifying it, your robot's still in production, which is pretty good.
You can, but we can't.
Well, you will if you take. You can't because you don't have the key. But we got keys. But if you take the what is it called? It's called manufacturing and computer simulation. That's where you get into this right here, if that's what you want. If you're in the robotic short, then that's required. If you're in the AUT, it's not required. If you don't want anyone. Well, it's good. It's a good program, but odds are you would not need it if you go to work, if you're a programmer for Camtech. Camtech don't use simulations. They do on the fly, but they don't modify their programs all the time, right? You understand? A lot of their robots are welding robots, which they have to reprogram. And then their transfer line, those robots are probably almost never reprogrammed. So all they're doing is just they're moving it from this press over to that press. Usually they either use magnetics or they use it's over in Maxwell. Camtech and Sealtech is down on exit 100. They do a lot of the Sealtech is here. I'm thinking about Plasti-Pac. Sealtech does a lot of the plastics for them. Bros is right down there by Mercedes. You see Bros on the inside of the interstate, but they have a lot of robots. But yeah, it's got bigger Bros on the side. Which we have an internship program with that company, but I think I forgot to call her wanting to know what shifts the guy's going to work. We have nothing to do with Bros. To get into that internship program, Bros picks the people to get through with that. We have nothing to do with that. We just teach the academic portion of it.
What is that place? Spell it.
BROSE. Just like it sounds. They make seats, basically seats. For all different types, huh? Oh yeah. So Bros makes them for, I think, about 3 or 4 different car manufacturers. They make those seats for them. But they're located right here off the interstate. So I know that's, but when I looked at the points, all those points are given a Cartesian system. Let's see if I can remember. It takes me a little while to get back into this. That's the pulses. See, this is in a Cartesian system relative to an origin. So when I record these points, when I record the points, they are relative to a system. So if I single step through the program, on this one it's not very hard. You can see the actual Cartesian system changing up there. So when I save that point, this is the way it was stored. It's stored in XYZ, which we have a basic understanding now, and then the orientation of the tool. Roll, pitch, yaw. We looked at that yet. So these over here are in angles. So roll, pitch, yaw is given in angles, and then the XYZ is usually given in millimeters. So that means right now, this is at this position relative to origin. This is at this position. So Y, we didn't move Y at all. I brought it straight down. This is Z relative to origin. And then the tool is dropped down 180 degrees. Roll, pitch, yaw. So that first one is how much, that's not roll. This one is pitch, yaw, and roll is the way it's given. So this is that Cartesian system that we were looking at. Now if I jog it in Cartesian, it's very similar to a rectangular robot. But it's real easy to jog in Cartesian, because if we jog it in Cartesian, I'm only concerned with a direction. So we can jog it here too, by the way, which we can't do with a real robot over there. So the simulation is going to give you a lot more tools to make it easier to program and get positions and stuff like that, which is really neat. If you're going to take that class, I think it's neat. You might not think it's neat. So robot classifications. We need to understand a little more robot classifications. So actuator, what's the actuator? The actuator is that device that converts a pressure into a motion. Basically, we have two categories of actuators. We have rotary actuators and linear actuators. So normally, the way a linear actuator would do, of course, linear means what? Anybody know? Straight. Linear means in a straight line. So if we move something in a straight line, I'm going to put a pneumatic cylinder over here. It can move a certain amount of distance. Well, as soon as it comes up here and hits that valve, that front part, it's going to stop. And that would be what we call the actuator stroke. So the actuator stroke is the maximum it can move from this end all the way to that end. So in linear actuators, the stroke is given in units, right? Like 100 inches or 100 millimeters, something like that. And of course, rotary actuators, the stroke would be given in degrees. So if it's got a stroke of, 270 degrees, that means you'd have 270 degrees of arc on it. Now, what we might want to do is, let's say it's got 100 millimeters. And then I want to limit the stroke. Well, what we could literally do is we could come out here and put something on the rod, and then I could put something mechanical down here, and then it would literally come up there and hit that. We refer to that as a hard stop. The device is used to stop the motion of the actuator before it reaches its full stroke. Now, if we went over there and looked at the big Fanuc robot, it's got its stroke on its axis 1. It's probably around 320 degrees. Well, the problem is those big glass windows over there are within that 320 degrees. And we don't want to have the person to have the ability to go past that and jog that robot into those glass windows. So what have we got on that robot over there? We got hard stops on it. So what we've done is we've limited that stroke so we can't rotate it that far. Right? You understand? So a hard stop is basically a piece of metal or hard plastic or something like that the motor would run up against, right, or an actuator would run up against to limit its stroke. Y'all understand that? Fixed hard stops. Fixed hard stops are there the same. They don't move. Variable hard stops means you can do what with them? You can move them. Yeah, that's one method. We have robots that run in automated machines. To say it has to be reprogrammable does not necessarily mean you got to go into a computer and change some code. We could just as well, if we got variable hard stop, we could change the stroke by going out there and doing what? Moving the variable hard stop. Well, that's programming. That's reprogramming the motion of the length of the robot. So there are some robots out there that would be reprogrammable, but the points are not done. The points are not done, especially the pneumatic robots. The points is not done in a program with a bunch of instructions. It's done by doing what? Going out there and moving these hard stops. Now you still have to have a controller because it's still got to decide which axis to move, right? You understand that as far as where, and this is real true on electric actuators don't like to be stalled. Get something in motion takes a bunch of power. So when you got a electrical actuator that's at a standstill, when you start it up, it pulls a lot of electrical current. We call it start current. Well, if you stall it, it's going to pull that same start current all the time. So what happens if we stall an electrical motor, most of the time, if we don't protect it, it's going to burn it up. Fluids don't care to be stalled. So a lot of your robots that are programmed on hard stops, they are pneumatic or hydraulic robots. But stepper motor. Stepper motor, this is a special DC motor that rotates in steps. And I'll have to get that. I'll probably next class before I can show y'all one of these. I can show you a big one that it's taken apart. But what we do is we send pulses to this thing, and for every pulse it rotates a precise number of degrees. This is probably one of the most popular motors used in open loop systems. What's open loop? Huh? That where the actuators don't provide feedback. That makes sense? So over one of these grippers are open loop. So a while ago, when I first turned that thing on, the program told the gripper to open. But the gripper didn't open because there was no feedback, and the controller just kept running the program because there was no feedback saying, okay, the gripper is open. Now, a lot of tools are run open loop. The advantage of open loop is it's cheap. The more electronics I add to my system, the more expensive the system's going to be. So it'll be hard to do in this class to go over there and manufacture line. We'll try to set up a line because Rick is doing the class over there. But you just see the systems that are open loop. That if something's not there, the robot don't know. They'll go over there and try to pick it up and do everything it's going to do, but there's no sensor to tell the controller that there's nothing there. And that's on several things. And why? Because the more sensors you add, the more expensive the system has. So if you add a sensor, then there's got to be something to monitor that sensor, right? A lot of open loop. Closed loop. By the way, the term we need to also pick up, the book needs to talk about that. I'm almost positive it's in the power supplies. But the technical name for an open loop system is non-servo. And then the technical name for a closed loop system is servo. Those terms are used interchangeably. So a closed loop system is a system where we have something out there that provides feedback. Of course, we don't like to use it as feedback, but one of our main methods of feedback is test. We would like to get feedback while the class is in session. I had one of my students who was going over a very complex integrated circuit called a PIA. We We went over it, any questions, went through that whole thing. Gave out a worksheet. One of the students says, I don't understand any of this stuff. We need to go back to the start. Never asked a single question in class. And I told them we can't go back to the start. We've already, right, you understand? That's like going and taking your driver's test and getting the seat. Said, can you teach me how to drive? What would the guy say? No. Hell. That's a true story. Of course, I still talk about that today. So it's up to you to give us feedback. You know, y'all paying for these classes. It always amazes me. So this is basic classification of control systems. Open loop or what? Non-servo, closed loop or servo. Then we classify the control system or the robot system according to a geometry. Of course, the geometry is the shape, right? And we have the basic shapes in robot systems that we do in physics geometry class. So what's the first one up there? Rectangular. Also could be called Cartesian, by the way. Go into Cartesian. Cartesian is a rectangular system. X, Y, Z. Now these are not a rectangle. These are rectangles, but they're solid, right? They have a volume in them. So they all have a up, down, left, right. So it would be a rectangular box. Then we have cylindrical, which we've already looked at. Then we'll look at a type of robot. This is a type of category robot. It is a cylindrical robot, but it's a jointed spherical. Jointed cylindrical. So it's not going to do a perfect cylinder, right? Because it's jointed. Selective compliant robot assembly. Then we have a spherical. So the SCAR robot would be considered to be a jointed cylindrical. Then we have the jointed spherical, which all our robots are over there. Drive power, we classify them by what drive power the robot uses. We understand that now that the controller has got to be what? It's got to be electric, right? So what we're talking about here on the power system, what power system does the robot use? So our robots use electric or servo motor. Servo motor, that's the term. What's a servo motor? It's a motor that provides feedback. That makes sense now? So if you're in radio control stuff, a little motor that moves the surfaces of tilt things, they call servo motors. Because they provide feedback to you don't come back to your radio, it goes into the system. Those things are pretty neat. And then the application, basically, the first two are probably the main one. Assembly or not assembly. Then we get into a bunch of classifications. Assembly, non-assembly, general purpose robots. So basically, all these robots here are basically what we call a general purpose robot. Now what is a general purpose robot?
Basic.
Yeah, what it does depends on what you want. All you got to do is figure out the tool and do what you want. That makes sense? And then mobile robots. We have a couple mobile robots. Y'all have all drones is a big thing in the military. We're fixing to get into autonomous cars and driving things. And those are really going to be what? Robots. How are you going to program it? Well, if you're going to go somewhere, you got to tell it where you're going to go, right? Well, there's something you're going to have to do besides just driving a straight line. You know, it's pretty interesting. It's going to be really interesting. That's going to be in my lifetime. Another type of thing we have is we have two classes of robots. All our robots are what we call point-to-point robots, which are point-to-point control, which is by far the most prevalent method of programming robots. So you saw a while ago on that simulation, how did I teach it? I just moved it into all the points. And then what we did is we specify how the things do the points. We got a video I'll have to bring up. I hope I can find it. Is that a continuous path robot, or continuous path control, is where we come up and we literally grab the robot, we put the robot in what they call a floating position, and then the programmer comes up there, usually a skilled person that's skilled in what we're trying to do with the robot. They literally move the robot through the path they want to follow. And the controller memorizes the path. Non-controlled path robots would be, I don't know what they're, well, look at that in the book. What do they say about that? I got your book. Yeah, it's good. Y'all remember.
Go to chapter 4 before it mentions.
So we're going right through the book. So this is robot classifications. I don't think I put the number, which I think would be robot classification 1 is the chapter we're working in, which is chapter 3.
Asking about non-control path.
Open loop, closed loop, variable stop, stepping motors, disadvantage open loop control, closed loop control, application of closed loop control.
I see on page 60 it talks about continuous path control.
It looks like they changed the book a little bit and got it out of the same order. So they're like continuous path. It don't look like that's in this chapter.
No, continuous path is on page 60.
But that's in chapter. Yeah, that's in 2. So we'll pick up a little more on that. I think everything else is okay. Intelligent level, is that still in this chapter? Of course, pretty low and high intelligence. Low intelligence, of course, these robots are not going to do that much, but they're going to be the cheapest ones out there, right? So the higher the intelligent level of the robot system, the more expensive it's going to be. We'll see if it's in this chapter. Like I said, this is
And classification by intelligence level also puts it out.
it's in chapter 4? Okay.
What 3?
Cincinnati Millicron, this is the OT3 robot. I don't know if this is used stick stops or not. This is what type of robot would this be? If we can tell. It's not a spherical.
Linear?
Well, that's not one of our,
Oh, I see.
that's not one of our
Yeah.
classes. You know, it's either going to be rectangular, it's going to be, could be cylindrical. From this, we can't tell if it rotates. If it rotates, it is cylindrical.
It looks like it has an axis.
Yeah, it looks like it has a bottom. But this definitely would not be a spherical because they don't have a tilt to it, right?
Yeah.
So to be a spherical, you got to have at least one vertical axis, rotary axis. Yeah, I think it does. Yeah, you're right. So there, I think that's the basis. So this would be a high technology closed loop electric power cylindrical robot. So it says it point to point, primarily used in material handling. So this is the way we would classify the robot. But what does it do? So this would be probably classified as a, say, non-assembly robot, right? Could be a general purpose because right on the back, right on the specification, it says it's what? Primarily used for material handling. What do you say? This robot is not in Cincinnati Millicron. It's not even in business. Classified by control system, open loop. We also, odds are, open loop is the term, but technically, just about every one of these guys are going to call. This is probably what you're going to hear technically more often. We have servo and non-servo. There's no feedback. So what's feedback? Back to you or back to the controller. So basically what we mean is that the controller tells an actuator to do something, and the actuator tells the controller to get it done. So if I want to move the tool center point on one of those robots at 100 millimeters per second, then how in the world would it know it if there wasn't feedback that's saying I'm going at this speed, right? I understand. So if you got, and we talked about this the other day, if you got cruise control on the car, as soon as you hit that, you are in a servo system. So there's some sensor somewhere. So your controller says go this fast, and then there's some sensor somewhere that says this is how fast I'm going. And if you say go 50 miles an hour and it says I'm going 40, then the controller would adjust for that, right? You understand? Because now it's got feedback. Of course, also these robots here, they have positional information too. Where the robot says go to this position, and then the sensor says, don't say I'm at this position. It gives it feedback the whole path to that position. And then once the desired position and the position matched, then the robot's going to do something. So we go between these. What's the advantage of open loop? Right? We have tons of open loop. One's really cheaper. What's the advantage of closed loop? Could say precision, but we can make things precise with mechanics. But we couldn't. So what's nice about this feedback is that we can make changes real easy without going out there and cutting out hard stops and moving hard stops and all this other kind of stuff, right? We don't have to worry about wear. Gary brought that up last class. You know, mechanical stuff always wear. So if I've got a hard stop out there and my robot's constantly beating into that hard stop, then what's going to happen? Well, it's going to wear, and if it wears, then my precision gets off. If I've got feedback, even if you have wear, it's going to go to the same spot because it says I'm going to here, and if you got wear, it's still going to go to the plot. It's going to go there. So these feedback sensors, they don't wear. There's no mechanical contact with them at all. We'll show y'all some of those later on. So we're going to take a robot. We're going to start at point 1. We're going to move it to point 2. We're going to pick up at point 2. We're going to move it to point 3. Pick up apart at point 3. Retract at point 4. Rotate to 5. Extend to 6. Drop to 7. Retract. Is this open loop or closed loop?
It could be either.
Yeah, that's the perfect example. That's it. It could be either. We could do this either way. We could do it. We could do it with mechanical stop. We could definitely do this with mechanical. All your points would never change, right? You understand? And we could do it very accurately. And there's a lot of automated machines that are non-programmable, and that's all they do. They do the same thing over and over and over and over and over again, and they don't need to be programmable. So there's still a lot of hard stops out there that appear to have intelligence. These actuators are just running up against what? Hard stops. They stop, and we still got a controller that will hold it there for a little amount of time. And then it'll lift it up and hit the hard stop up here. But every one of these could be everything here could be hard stop. You're one of the first persons that's got that right. Just about every time I do that, they say, closed loop. Open loop, robot is placed in the correct position by the actuator stroke, by fixed hard stops, variable hard stops, stepper motors, or timers. Timers are okay. So the first robot y'all going to program, these are open loop robots. So what do? Well, we run them with timers. So we say run axis 1 a certain amount of time, and run axis 2 a problem we have with these robots is they run off battery. What's the problem with battery? Yeah.
They slow first.
Yeah. So y'all teach y'all's program. I think one program you're going to teach is you're going to come over and swing the robot. You're going to go down. You're going to pick up a block. You're going to raise it up and move it over through. Put it down. I think another one is try to stack blocks. And if you get close, guys, we're okay. We're just looking at this because these robots, they're open loop. Now, if we ran them off DC power supplies, they would be a lot more accurate. Since we're running off batteries, by the time you get over there, odds are the batteries run down a little bit. We're running them off timers, so we run the motor for 3 seconds, and the motor don't run as fast as it did the first time. It's not going to make it the second time. So y'all remember that when you do that. So this is 3 methods. These are all open loop. Okay, so we already talked about linear actuators and rotary actuators. Are we okay there? So what's a linear actuator? These are actuators that generate a force in a straight line or move in a straight line. Rotary actuators, these are actuators that move in an arc. These could be, they can be electric. Usually, anything, we do have electric actuators. Normally, when we use a rotary actuator, electric rotary actuator, we need an actuator that cannot rotate past 360 degrees. The other term, anything that rotates more, we call a an electric motor can definitely run more than 3. It can make multiple turns of 360 degrees. Right? So usually, when you talk about electric actuator, we're talking about one that's less than 300. So the rotary actuator is one less than 360 degrees. Even pneumatics, if it goes multiple turns of 360 degrees, we call them pneumatic motors and hydraulic motors. So normally when we're talking about actuators, we're talking about the stroke is limited to less than 360 degrees. Are we okay there? So these are cylinders. We call them cylinders because they're round. And then what we have, this is what we call a double acting cylinder. Because what we do is we come up here when we put pressure on one side, not on the same time. So if I put pressure into this side, it's going to cause this cylinder, the rod, we call that the rod. We call this the piston, by the way. We use a lot of terms that we do in automobiles. So the rod would push out, and then if I wanted to make it go in, we call it extend. The rod would extend. Then what would I do? I would take this pressure off here, then I'd apply pressure right there, and then this is going to push that piston back in that direction, which is going to cause the rod to retract. Now, what limits the stroke, of course, is the cylinder itself. But when you start looking at these linear cylinders, they give you the stroke. They say, okay, if they say it's 6 inches, then that from all the way retracted to all the way extended, the tip of that rod would move out 6 inches. And we called it a double acting cylinder because we use pressure to move it in both directions. We called it a double acting. If I was to come up here and put a big old spring in here, then I could come over here and put pressure on this side, and then it would cause it to push that way. And then if I took the pressure off, it would cause it, the spring would do what? We call these single acting cylinders. And they're both of them very popular. Single acting cylinders are cheaper, the control of them is cheaper, because we don't have to control the pressure in 2 directions. So in fluid power, we have these things called directional control valves. And that's what they do. So you shift it one way, and it would route pressure to one side, and it would exhaust the other side, right? You understand? And if you shift it the other way, it would cause the cylinder to move back in. So here, that would be a little more complicated to control, the double acting cylinder than a single acting cylinder. Single acting cylinders are used all over. You got a hydraulic car jack, that's a single action cylinder. So you pump it up, but you depend on the weight of the car to do what? To retract it. And that's a single action, that's a fluid power, that's a hydraulic single action. So single acting cylinders, we use our pressure to cause the actuator to extend, and then we let something else bring it back, either gravity or a spring. And there's tons of these up there. Now, if we was to come in now, all of a sudden, what have we done here? We put in what we refer to as hard stops. So what have we done with our hard stops? We've limited the stroke of that. As far as the hard stop. Now, what this is most of your linear actuators. I think all of them we got on our manufacturing lines use the actual actuator stroke. Well, we could definitely do that. And if those was variable hard stops, we could reprogram them, right? Just by doing what? Just going out there and moving them. Yeah, if you're going to program these things, you're going to have variable hard stops. Your hard stops are going to have to be within the stroke of the actuator itself.
So when you say hard stop, you're referring to when you stop the machine, like an emergency stop.
No. I'm talking about taking something and beating it up against something to make it stop. So this is.
It seems to me that we use it in two different references.
Well, we don't call that a hard stop. We call that an e-stop. And what you got to understand is number one, we use the same terms in different trades. They mean different things in different trades.
Okay.
So when I'm getting together, we have a lot of terms in this class. But what I'm trying to make for you, and I'll put it up there this weekend. If y'all study for this, we have a glossary, but that glossary is relative to robotics, right? So we have a lot of terms that we use in robotics. We use them all the time. So one thing you got to learn to. So I don't know how to say that. I wish I could come up with an example. I'm talking about it. So just like you said, we use the term hard stop. I didn't use the term hard stop over there. I used the term e-stop.
I thought there was hard stop and e-stop.
Well, it is a hard stop. There is a hard stop. There are hard stops on the FANUC robot. There's big old to limit the stroke of the robot. So yeah, you're right there. And I'm not using them different. And they're variable hard stops.
So this is what you were talking about.
Yeah, this is exactly what. So we'll go over there and look if y'all want to. And show you all those hard stops, but they're variable, which means so what we're doing is we're limiting the stroke of the base.
So like, first thing we can do,
No, there's no hard stops on these right here. A hard stop would mean I'm banging the robot up against something to make it stop.
Oh.
Okay. Mechanical. It's physical. A hard stop is physical. Right? You understand? So you go out there and if you go out there in your car and you press that brake pedal, it's going to stop. Right? You understand? Yes. Well, it's running up against some hard stop. Right? You understand? Right? But it's not variable right now. Okay. This is not a computer. We're talking about mechanics.
So the hard stop would be inside.
This is a robot right here that runs. This is a robot here that runs on variable hard stops. So right here, there's a hard stop. Right here, there's a hard stop. Right there, there's a hard stop. So what happens is the robot moves until it hits a hard stop. These are usually open loop robots, and they usually run off fluid power. It's a physical thing. So if you was to start your car and drive it up there and hit that wall right there, that would be a hard stop.
Yeah.
And you can leave your gas on it, not gonna burn up your tires, but you're gonna stop unless you got enough power to get through these concrete blocks. So a hard stop is a physical means of stopping something that's in motion. An example would be a wall.
Pressure is such as
Yeah.
you said it was.
Yeah, well, that would be the engineering. You have to put a hard stop out there that's not going to be destroyed by the amount of pressure. Now, what we've done with the FANUC, since it's electric motors, when it hits that hard stop, it energizes the switch, so it cuts off the motors. Because if I stall that electric motor, it would burn up. So let's go. Like this, I'll have to show y'all one of these motors. We got several. I can show y'all. No, I can't show y'all. Correct. So I'll set this up for you. We're fixing to go to the lab anymore. Go to the lab anyway. But a stepping motor is a DC motor that rotates in what? Yeah, steps. Usually rated in number of steps per revolution or number of degrees per step. So if I had a 720 step motor, then if we divide that into 360, that would mean I would get 0.5 degrees per step. We use this thing. What's nice about this guy is we use this thing a lot in no-flow systems. And you probably use one of these pretty often. This is the motor they use in a lot of printers. And they got a lot of printers. Inkjet printers, laser printers. And what they do is they start from an origin. If you know a starting point, then you know how far we can move per step, then we can control this thing precisely. We just have to start it from the origin. So anytime you turn your printer on, what's the first thing you hear it do? Right? Well, what it is, it's hitting a sensor over on the usually on the left-hand side, and it hits that sensor, and it says, okay, that's 0. And then from then on, we can control this position by steps. Paper feeds usually done like that. That's really easy to see. You can actually see they can start and stop that motor anytime they want. So when you put that paper in there, it goes up there and hits that front end sensor. And then on, it knows an origin, right? And it knows that it goes down 500 steps, it's halfway down the path. So stepping motors are used a lot in open loop systems. There are some situations where they have servo stepping motors. Those guys are very, very expensive. We got a guy, anybody know Thomas Hickenbottom? A unique person. Thomas has designed and built 3D printers. Well, he's making them from scratch. Now he's printing parts to make the printers. Pretty neat. So, Thomas. He makes them from scratch. We'll find the parts and put them together. I'll show y'all some parts. He ran me a jet airplane on the street. And then there's a thing over there in there. You can build a lot of these. You probably could make the 3D printer. You could make a lot of the parts for a 3D printer. You can't print a stepping motor. A stepping motor right now is made out of metal. It's got moving parts and stationary parts, which is all the gears and everything, all the gears and the platforms and stuff like that, plus the slides that the motors step against, those have to be steel also. But all your gears, and that's what he's starting to do, the gears and the mounts and all that other kind of stuff. He originally bought them from different places. And now all the gears and stuff on there, he's bringing. Yeah, he's good. He's in the 82. The printer they're using over in the MillSouth building is a silicone printer. It's basically real fine sand. What they do on that 3D printer is they print it in layers. What they'll do is they'll take a adhesive and they'll pour it around the layer, and then they'll put another real thin coating on there, and then they'll do the same thing, and they build it up a layer at a time. Then what they do is they'll take it out, they'll dig in the sand, pick it up, dump it out, and they'll have that's done, that's silicone. Sand print. The 3D printer that Thomas built is what called it's a plastic string printer. So it uses a string very similar to weed eater pulp. Then it comes down and it does layering too. It's got a print head actually melts the material and lays it out in a certain precise thickness. And then it builds things in layers too. The problem with string printers is they're a lot cheaper, but you can, it's really, really hard to get smooth because string. I can show you. But that's done with stepping motors. But what he does is that every time he fires his printer up, he runs it against hard stops. So it's 1,000 steps. A stepping motor don't care if it's stalled. So because it's doing it in the steps. So if he's got 1,000 steps across there, he does 1,002 steps. The thing would come over here and hit against that hard stop. Now that hard stop would be the zero reference, right? And once he's got a zero reference, if he wants to move it so long, he can transfer that into steps, 2,000 steps. Then move out 2,000 steps. It would be almost perfect. So 3D print, stepping motors are used a lot in 3D printers. It's one of the cheapest ways to do it. But if they ever stall, this open loop, if something happens and they ever stall, for some reason, they don't know it. They'll still go 50 steps this way, 40 steps that way. So you got to make sure. And your printer does that every once in a while. Printer, you get a paper jam in there, and it's lost its step. And it might try for a little while, but then again, it'll come back over and find itself. It's knows it's stalled. Because if it ever hits the end sensors again, there's only one reason it would do that. Why it's stalled. It cripples up your paper and all that other kind of stuff. That don't happen much anymore, thank goodness. So these motors are really, really slick, and like I said, we'll hook one up to a microcontroller called an Arduino, and run a stepping motor for you next class, and let you set things in the steps, and then we'll speed it up and let you show you what it can do. And I got one program where I can say 90 degrees, and that motor goes 90 degrees. And I can say I can enter the degrees I want it to turn. It turns those exact degrees. I can say 720 degrees, and it can spin around twice, and stop right at the very top. All it is just step.
So it's always clockwise.
No, you go. You send the steps in a sequence. It has 4 coils around it. Electronics, what it does is it steps it around that thing. Well, if you change the direction of the steps, I think I got a picture in here. This is out of my book, by the way. Yeah, this is a stepping motor. So you can see what they do is they rotate the field around there, but they rotate the steps. And it moves to that step. And then we come over here and move it again, Well, if I change the order of the rotation, the motor goes out. Huh? These guys,
I had just had an efficient
And this would be 25, no, this would be 360 divided by 4 per step. But you got to understand, I can keep putting multiple poles in there. The closer I make the poles, the more precise the steps are. So I think the stepping motors that we got, that I'll show you, these are 24-step motors. So that's 15 degrees per step. So they have very low rate of revolution. You can get these things up to 1,024 steps per revolution. So your degrees per step would be extremely small. In certain motors, you can do what they call half steps, if you control it right. So if you got 720 degrees, if you half step it, then you'd have twice that many. So you can do what they call half step. Which what they do is they energize two coils, so they'll energize this one, and they'll cause it to move to here. And then they'll leave this one energized and energize this one, and it'll move it directly into the center. And then you'd turn this off and leave this energized, and it would move to 3, and that's called half stepping the motor. So basically, if you half step the motor, you get twice as many steps per rotation as you do. These things are neat. They're really cool. And we've got one on our Amatro line over there that's positioning a carousel over there, and it's a stepping motor. So we tell it to move once it finds its origin, and we'll show you how it finds its origin. Once it finds its origin, we can tell it to move 90 degrees. Well, we don't tell it to move 90 degrees. Our computer would take 90 and divide it by the number of steps and send those many pulses and stuff. I'll let you show. So open loop. This is an open loop control. We still have to have valves and stuff, but the open loop robots would basically depend on hard stops, right? And if it's going to be reprogrammable, those would be variable hard stops. Now, if I'm going to a closed loop system, it's going to add a lot more to the price of the robot, because now we're adding sensors and we're adding a section on our controller that monitors those sensors. So here's the advantage of open loop. You can't say it's not highly repeatable because it depends on those hard stops. Those hard stops are very accurate. And like I said, there's automated machines that's been around for years that depends on hard stops. Disadvantage. Well, if it's open loop, we don't have speed control, so we're depending on the flow rate of the fluid. Okay, if we want to reprogram it, we have to literally go out and do what? Yeah. And if it's not reprogrammable, that means the position of the things inside the work cell is critical. And that's still true even on these, by the way. I don't know why. If I'm going to run an open loop system, and the robot is closed loop, and it's going to swing over here and pick something up. Well, if it's open loop, then this guy down here has got to be in a perfect position for it to pick it up, right? You understand? Yes or no? And we'll go over there and look at the line and look at some of those jigs where parts fall into a certain position. All the robot knows is to go to that position, and it's depending on that device to be at that place. Why don't we put a sensor out there? Because if I put a sensor out there, then that's going to do what? Cost me. So guys, we're going to stop right here.